Okay, so hi everyone. Welcome back to another episode. It's the second episode in this YouTube series called Decoding Ancient History. Today we're going to be looking at the Richat Structure in Mauritania. In particular, we're going to be using the C++ programming language, and we're going to be applying the flood fill algorithm to the Richat structure. So how do we do that? We're going to be using a digital elevation model. And so a digital elevation model in simplest terms is just a 2D array of heights or elevations. And it's most convenient for us that the STS-99, the Space Shuttle Mission in February of 2000, also known as the Shuttle Radar Topography Mission, so that was STS-99, February of 2000, was able to collect a lot of terrain data over at least most of planet Earth. It collected about 9 terabytes of interferometric C-band synthetic aperture radar, or SAR data, and it was stored on over 14,000 compact discs, or CDs. Because I guess back then they were using CDs in 2000. Well, anyways, yeah, all the data that was collected from this shuttle mission, basically they're able to put together a digital elevation model of the entire Earth, or at least most of planet Earth. I think it's roughly 30 meter horizontal resolution, if I'm not mistaken. Maybe it's 90 meter, actually. But we're going to be using some of that data, and it's some of that data right over the Richat structure in Mauritania, and seeing how the Richat structure may look if it was flooded many, many years ago. So some people think that the Richat structure was home to the ancient lost city of Atlantis, like the capital city of the Atlantean Empire. You've had different YouTube channels suggest and popularize this theory. I'm not really sure myself. I do believe Atlantis existed, but maybe there's some other candidates as well, like the Doñana National Park in southern Spain, the Andalusia province. I think that's a good place to look. I think there's another plateau in Morocco. Maybe I'll do a future video on that. But here we're just going to, again, apply the flood fill algorithm to the Richat structure to see how it might have looked if it were flooded with water. It's pretty widely speculated and even accepted that many thousands of years ago, the Sahara Desert was a lot more lush and tropical, covered with lakes and rivers, and it's always very interesting and fascinating to me. And it wasn't even that long ago, allegedly, right? Maybe 10, 12, 13,000 years ago. There might have been a lot of water in the Sahara Desert. So let's go ahead and get started. Let's get with the coding. We're going to be using C++, the C++ programming language, as well as GDAL, the Geospatial Data Abstraction Library, and GDAL has an API for C++. So let's go ahead and pull up Visual Studio. Actually, one more thing before we start coding, and so you can actually download the DEM data, digital elevation model data, from the Space Shuttle Topography Mission, the Shuttle Radar Topography Mission. You can download it from the U.S. Geological Survey. That's earthexplorer.usgs.gov. So that's you can download it here, and that's where you can get the data. In this case, I'm going to be using the data in the form of a GeoTIFF. So what I have here is a utility class, a C++ utility class. It's geotiff.cpp and then geotiff.h, the relevant header file. And this geotiff.cpp, this class just has some convenient methods for reading a geotiff file. That's going to be storing our digital elevation data. So we already have that here. It's subsetted _final.tiff. But yeah, there's some methods here. In some methods, get the file name that was passed into the constructor, get the projection as in the form of a string, get the geotransform, a 6-element array of doubles. You can get the dimensions. There's also a method to write a geotiff out. and also get the array data in the form of a 2D array. So we're going to be using this utility class, the C++ class, when we do our coding here to apply the flood fill algorithm. So let's just go ahead and get started. Let's get coding. So I guess I'll just call this I don't know, Richat fill.cpp. Save it as a new file, and yeah, let's go ahead and have some fun. Let's get coding. So the first thing that we're going to want to do when we define a C++ source file is we're going to have a main method, I suppose. It's going to return an integer, so we'll just return 0 for now. We're going to have some imports here that are going to be probably fairly useful for us. Some standard built-in C++ libraries. IOStream. We can include the built-in string library. Let's see here. We can include a header file stdlib.h. What else can we do? We can include stream. I forget exactly what this does, but we may have some use for this module in the future. We'll see. File system may be useful as well. We'll see. I mean, even if we don't use these, it's not a huge deal. For now, I mean, again, we're just having fun here. You know, the point of this YouTube channel is to apply programming to ancient history, to visualize how the Earth may have looked in different places, and maybe even learn something about ancient civilizations. You know, that we're just having fun here, you know. We're going to want to include also the tuple library and the set library. So these are also built into a later... in the Python programming language, you might see tuples and sets. Those are built in, but they're also built into C++ as a later addition. So you get some updated data structures here, which is a good thing for C++. Let's see, we're also going to want to include our geotiff class, our utility class that we wrote. We'll include the header file so we can use it. We can also define a string, std string, as simply as string using a type def. And last but not least, we're going to have to define an elevation threshold. So this is our cutoff for when we apply the flood fill algorithm. Elevation thresh. We'll say it's about 440. I think that was what I used when I was testing out some of the when I was looking at the image file itself. So we defined a constant here. We imported a bunch of libraries. Let's continue on. So what we can do here is we can scroll down to the main method in our C++ source file. And actually, before we continue, let's make sure that this file at least compiles. I think that's a good idea. So I already have a compilation command saved. But what we can do here is we can copy this, and of course we have to replace dem floodfill.cpp with the one that we're creating, Richat _ fill.cpp, and let's just make sure it at least compiles. And it appears to compile with no issue. Good. So we're not, hopefully not doing anything too silly here. So when we're applying before I continue here, another thing I'll mention is that we're not going to be using the recursive flood fill algorithm. Recursion can sometimes blow your stack, especially if you're applying it to a 2D array. So, you know, that can be kind of harsh on the memory. What we're applying here is something called the breadth-first search BFS. Breadth-first search BFS with a Q flood fill algorithm. So we're going to be using data structures here, sets and tuples. So I don't think we have to worry about memory here. At least I hope not. We'll define our starting coordinate, our starting x coordinate, start x. We'll say 0 as a default value. our starting y coordinate is also a 0. We can also define the elevation threshold. No data value, that is. Elevation threshold. I'm not sure if we're going to use this, but there is a no data value here of -9999. That's present in the geotiff file. In fact, I wonder if I do a gdal info of the subsetted geotiff subsetted underscore final.tiff, and I wonder if it has a no data value. Or fill. Maybe sometimes it's called fill. No. Well, I'm pretty sure it's -999. So we're -9999. So we're gonna go with that for now. We're gonna define some command line arguments here. So actually, what we need to do is we need to add that into our main method as arguments. The number of arguments argc, as well as an array of a C++ array of our arguments. So we're going to update that there at the top. So the first command line argument here, what we can say here is going to be the starting x in the form of a string. That's going to be argv2. So we set start x and start y up here. The default values are 0 and 0. But we're going to overwrite those later on with the command line arguments. So let's go ahead and continue. So we got start, I don't know, y str, I guess, argv3. The output directory to store our result. Our result file output file will be also a geotiff. It's going to be basically a geotiff containing ones and zeros. You know, the ones are areas of flood, so to speak, and then the zeros are areas of non-flood. And so we'll say that's I don't know, outdir, and that's going to be argv4. Okay. And we can go ahead and overwrite the starting x and y values. We can convert to integer. The input argument from the command line, start x string, start y is atoi. So atoi converts the string to an integer. Again, y string. So we're going to convert both of these. Okay. And then let's see, what else do we have here? We have to define, we have to get our input geotiff file that we're going to pass in via the command line. So we're going to pass subsetted underscore tiff here as a command line argument. So we're going to need to grab that. So we can see our constant char. So this is a pointer to an array of characters. And we can say here tiff name is equal to argv1. So that's going to be the first command line argument. And then we're going to create a geotiff object out of that. So we're going to call the constructor here. So again, in geotiff.cpp, what we have is a constructor where we pass in the file name of the geotiff that we're reading. And then, you know, it'll open it up as a GDAL dataset, a pointer to a GDAL dataset. And then it also fills in the dimensions here, the class variables. So then, we're going to create an object here. We're going to pass in tiff name, okay? And what else do we have here? We can, next, we're going to read some basic parameters of the geotiff. So we're going to get the dimensions of the geotiff in the form of a 2-element array, a pointer to a 2-element array. So really, the pointer is just the memory address that points to the first element, or stores the memory address of the first element of the array, by the way. But anyways, we're going to get the dimensions here. It's going to be, let's see, the pointer, and we can use the arrow method get dimensions, right? We're also going to need the DEM data itself, which is integer type. So we're going to use the memory address of the geotiff object, and we're going to call get array data, right? Get array data. Yep. Okay, there's no arguments there. These are all instance methods, and then we can define the number of rows and columns. So the number of the number of rows is going to be equal to dimensions 0, and then the number of columns, end calls, is going to be dimensions 1, the second element there. So the next thing that we're going to have to do here before we are able to write our method that performs the actual flood fill algorithm itself is we're going to have to define a binary mask of ones and zeros. So we can use the character type, the char type. It's going to be a 2D array, so a pointer to a pointer. Mask, we'll call it mask, and then we're going to say new char, and then we're going to basically the number of elements is going to be the size of the char. I guess that's 1 byte times the number of rows. So we can go ahead and do that. We're also going to have to allocate memory. So for each row, we're going to have to allocate the data for each column in the array. So we're going to set up a for loop here. We're going to iterate through the number of rows. So we can say in r equals 0, r less the number of rows, and then we got to increment r. We can say mask of r. So for this row, it's going to be a new char, and then we're going to fill it in with the number of columns. So yeah, so right here we just basically set up a new 2D array, a pointer to a pointer, a 2D array of zeros of the char type. So char is we don't want to use int, it saves memory. If we're only going to be using ones and zeros, char is more than sufficient here. So after that, all right, and I guess before we write our method that applies the flood fill algorithm, what we're going to do here is we're going to deallocate the memory of this mask. Yeah, so we're going to iterate through the rows again, and call the delete method to free up the memory there so we don't get any memory leaks. I'm not really using smart pointers here, and to be honest, I'm kind of a novice in C++. I mean, I've played around with smart pointers a bit, but I got to learn more about them. I'm sort of just used to using new and delete, kind of the old school way. But I definitely got to kind of learn more on that and learn more modern techniques of C++. So, you know, I always accept criticism here, but again, we're just having fun. So let's go ahead and free up the memory for mask, and then we're going to, of course, we're already returning 0. So the next thing we want to do is really the heart of this video. We're going to be writing a new method here that actually applies the flood fill algorithm, non-recursive again. So let's go ahead and start writing that method. And we're going to put it above main here. So we're going to call it void. For now, it's going to return nothing. In the end, I think it won't return anything. So the return type here can be void. We're going to call this method, I don't know, flood fill. We're going to pass in our binary mask of ones and zeros. Actually, it's going to be zeros when it's passed in. So it consists entirely of zeros when we pass it in. But we're going to pass in our mask that we're going to be writing over and writing with ones for areas that are, quote, flooded, quote unquote, right? And we're also going to pass in the number of rows, the number of columns, so n rows, n calls, the starting x coordinate and the starting y coordinate. What else do we have here? The DEM data, we're going to need that, you know, the actual DEM, the height data itself. That's a 2D array. It's an integer, so we'll call that DEM. And then we're going to need the threshold, which, I don't know, I'll just set it as a default argument here of elevation thresh. So, here we go. All right, so this is our new method, and let me just put this on a new line so we can actually kind of see it better. All right, I think that's a little better. So, yep. Now, what we're gonna do here, the very first thing that we want to do is we're gonna define two sets, two C++ sets, and each set is going to contain a tuple. Well, it could possibly contain multiple tuples, and in each tuple there's going to be two integers for the y and the x coordinates, or the row and the column coordinates of pixels that are filled in and pixels that are not filled in. So we need two sets. So we're going to define our first set here, std : set. It's going to be of type tuple, and it's going to hold an integer and another integer, again for the row and the column, and we can just call this filled. And for the other one, it's also going to be a set, and it's going to be a tuple, again an integer and an integer, and this is going to be fill. Okay, so I don't know, I'll just put a comment here. 2 slashes. We're not using Python. This is C++, so we have to use 2 slashes for a comment. Excuse me. So filled here, so this is going to be, I don't know, holding pixels already filled, right? This is going to be holding pixels that need to be filled. All right, so we got 2 sets here. All right, let's continue on. So the first thing we want to do is we want to call, so for the set where it's holding pixels that need to be filled, we're gonna start by filling in the very first coordinate, the starting x and the starting y. Okay, so what we need to do here is we're gonna say fill dot insert, and we're gonna insert a tuple. So we got to create a new tuple, so we can call make tuple, and we're gonna call sy and sx. And I think that should be okay. So again, we're starting with the starting y coordinate, the row, and the starting x coordinate, the column, and we're gonna mark that as filled with a value of 1. So we need to say here mask sy, the row, and then the column is equal to 1. So we got to mark that as 1. That's our starting point for the flood fill algorithm. All right. So again, when we pass in mask, it's going to be filled with zeros, right? But the areas of flood fill, we're going to want to turn those into 1s, right? So yeah, exactly. The areas of flood fill will be 1. The next thing that we want to do here is we're going to go ahead and create a while loop, and we're going to say while fill the set that holds pixels that need to be filled. So while fill.size is actually greater than 0, because we're going to be removing elements off the end, as we're going to see below. But while it's greater than 0, while it's greater than 0, we're going to get the very last element, the last coordinate, the very one at the very end. We're going to go ahead and grab it, and we'll call it std. It's going to be of type std tuple again, standard tuple. It's going to be an int and an int, and we'll call it last, I don't know, xy. We got to get the value at that memory location, the pointer. So this is a pointer, but the star here denotes that we're actually getting a value at a specific memory location. And then we're going to call the rbegin method, so the right side. So if you think of a set going from left to right, if you call the rbegin method, I suppose that you're going to be starting from the right side or at the very end, right? If you're going from left to right, you know, if you have a set, right, that you're filling in, you're going from left to right. So the left is where you start, the right is where you end. To get the last element, you're going to have to start on the right side. So we'll call the rbegin method here. And From this last xy parameter or variable, we're going to go ahead and grab the y coordinate, the last y coordinate, and the x coordinate. So we'll say here y. We can call the get a method here, and then we're going to pass in last xy. Same thing for x. So x is going to be, again, the column, and then y is going to be the row. Get 1 last xy. All right. Once we've obtained our y and x value at the very end of this this set, we can go ahead and pop off the this element because we don't need it anymore, right? It's already served our purpose here of filling in the filling in our mask, as we're going to see below. But we can pop it off and get rid of that last element. We can call the erase method, and we'll get the previous element to fill.end. So the previous method, we're going to say fill.end. And once we've sort of typed all this out, I'm going to try to go over this code a bit more. All this code is going to be in the GitHub account that's going to be linked below the video. So you can take a look at that if you want to and study the code more. So what we have right now is a while loop, and we're saying that while the number of pixels that need to be filled is greater than 0. Basically, yeah, that's what we're saying here. While the number of pixels that need to be filled, that list is greater than 0, we're going to pop off the last element in that list of pixels to be filled. We're going to grab its y and x values for use later down below, which we'll get to. And then we're going to erase that last element because we don't need it anymore. We don't need to look at that element again. Now, before moving on with another while loop, a nested while loop, so we're going to have a while loop within a while loop. But before moving on, we need to do a couple simple checks. We need to make sure that this y and x that we just grabbed here at lines 27, 28, we need to make sure that they're within the bounds of the image. Okay, so we're not going off the grid, right? You know, into column 1 million and row 1 million, or -5. We can't do that. So, excuse me. What we need to do here is make sure the y and x are within the domain of the image. So we can say here if y is equal to n rows -1, or x is equal to n calls -1, right? Or x less than 0, or y less than 0. So any of these conditions, if any of these conditions are true, oh, that's strange. Hold up. I'm just making sure I don't have any syntax. I'm using Visual Studio Code here, so I think that looks okay. At least I hope it does. I don't know why it's highlighting. Let me just see if this compiles. Let me... Okay, so we're clearly getting a compilation error here. And so why is... Oh, okay, I know what's going on. We have an extra parenthesis here. We don't need that. So let's go ahead and... Okay, good. At least when it comes to compiling with C++, it checks for syntax errors at least. And by the way, we're using the G++ compiler here. It's an open source C++ compiler. It's pretty well known. Highly recommend it. And if anyone's curious, I'm using Mint Linux here as my operating system. I find it very simple to use. Okay, so the next condition that we're going to want to check is to check if the DEM, or the height value at this row and column, if it's greater than or equal to the threshold of 440 that we defined above. And 440, I believe it's in meters. above sea level. But yeah, if it's greater than or equal to thresh that we passed in here, then we're also going to want to continue. So again, so we have these two conditions here in this while loop, right? So if it's outside the bounds of the image, or if it's greater than or equal to the thresh, we're going to simply want to move on to the next iteration. And I hope that makes sense to everyone or anyone watching this. All right, let's move on. I kind of want to keep this video brief, so let's get to the next while loop, right? Actually, my mistake. We're not going to write another while loop. We're actually just going to write another if statement here, so my apologies. We're not going to have a nested while loop. We're not going to have a while loop within a while loop. We're actually just going to have another if statement here, just below this. So what we can say here is if mask, our binary mask of 1s and 0s, if mask is equal to 1, so if it's already been filled, okay, then we can go ahead and update the 4 neighboring pixels around that filled pixel. So if we have a pixel that's already filled, it has a value of 1, then we're going to want to set the 4 neighboring pixels, top, bottom, left, and right. We're going to want to also set those pixels to 1. So what we can do here is we can say here, mask y and x minus 1 is equal to 1. And then I'm just going to copy and paste this 3 more times. We can speed this up. And then we can say here it's x plus 1. Down here is just going to be x for the column. And then we're going to say here y minus 1 and y plus 1. Okay, I hope that makes sense. I think in my original code here, I had a mask y and x is also equal to 1. I think this is redundant, right? Because if we enter this if statement, then y and x should already have a value of 1, because that's the condition, right? But I'll put that there anyway, but it's probably not needed, I don't think. So we just filled in the 4 neighboring pixels. So now that we've done that, we want to update our filled set that we defined above here. So this is a set that's going to be holding our pixels that are filled. It's basically, it's holding our row and column coordinates for those pixels that are already filled or have a value of 1 inside of a mask here. But what we're going to want to do here is we're going to update that. We're going to insert a new tuple, and we're going to use here y and x. All right. After that, what we're going to want to do here is we're going to want to create 4 Boolean variables to determine if the north, south, and east and west pixels are inside this filled list, so to speak, right? So yeah, again, we're going to have to check if these 4 pixels are already in the filled list of coordinates. So what we're going to want to do here is we can say const bool, I don't know, south filled equals filled dot find make tuple. We're going to say your y minus 1, right? Because we're looking at the southern pixel, x not equal to fill.end. Okay, so we're checking for membership here. Hope that makes sense. And we're going to repeat this for the other 3 neighboring pixels. So I can just copy and paste, right? A couple times, and let's just rename these variables as appropriate and update the coordinates. So we're going to say here south filled, north filled, east filled and west filled. It's going to be y minus 1, y plus 1, and then this is just going to be y for east and west, because we're looking at those coordinates to the left and right, and then we can say here x plus 1 and then x minus 1. Okay, hope that makes sense. Now we're going to use these Boolean variables now, and we're going to go ahead and insert, if any of those are true, what we're going to do is we're going to insert those coordinates into our fill. So actually, I'm sorry, if any of these are false, let me just be clear, if any of these 4 Boolean conditions here are false, then we're going to go ahead and we're going to add it to the fill list. So we're going to add it to the fill set that holds pixels that need to be filled if any of these are false. So what we can do here is we can say here, I don't know, if not north filled, we can say here fill dot insert make tuple y, sorry, we can say here fill dot insert make tuple, we're going to say here y plus 1 and x, and semicolon, and we're going to repeat that 4 times, well, 3 more times for the other coordinates. So let's just copy this and paste it 3 times. So if not north filled, what is this one going to be? If not, well, south, right, east, and west, and it's going to be y minus 1, and then it's just going to be y x. If we're going to the east, it means we're going to the right, so it's x plus 1 in our array and x minus 1 for west for those coordinates. So I think that's looking pretty good. I think that's all we have to do for this C++ method. And what we can do here now is we can go back to our main method, and we need to call this method. And I think it looks pretty good. We're going to see if it works or not. So we're going to go back to our main method here. And last but not least, what we actually need to do, so we're going to call the main, we're going to call the flood fill method, and we need to pass in our mask. So this is going to be our mask of, it's going to be 1s and 0s, areas of flood fill, areas of not flood fill. We're going to be passing that in to be overwritten. It's going to be overwritten in the method flood fill again. Got to pass in the number of rows, the number of columns, the starting x coordinate, and the starting y coordinate, and the DEM. And actually, we don't have DEM here. It's we need to get that variable. No, actually, I'm sorry. We already defined DEM above here. So that's DEM. That's going to be our 2D array, integer array of elevation values. Again, I think it's in meters. So from the Shuttle Radar Topography Mission. And so we call flood fill, and then after we're done calling this method, it should fill in our mask and mark as 1s the areas that are, quote, flooded, quote unquote, right? Okay, so we're going to want to write the result to a file, a GeoTIFF file, so we can say here string out name, and that's going to be write a string. We're going to take our output directory, so we're casting our output directory here, which is a constant char, like a pointer to a character array, and we're going to be casting it to a string here down here. This is called typecasting. Our output directory, and I don't know, we'll just call it I don't know, output, result, Richat, I don't know, flood, filled, it's kind of a long name, but .tiff, alright? So the output result is going to be a new geotiff. And we can write that geotiff by using our geotiff class, our C++ class, or utility class, if you will. We're going to be calling the let's see here, the write geotiff method here. So that's going to be useful. Again, all of this is going to be in the GitHub account linked below the video. So if you want to take a look there, have any suggestions for code, I'm always open. But again, I'm just screwing around here and having fun. Am I allowed to do that? Can I have fun programming? You know, maybe as a hobby. I don't know. All right, let's continue. So let's write out the result. We're going to call it write geotiff, and we're going to pass in the out name, which is a string. We got to pass in the projection. Yeah, tiff.get projection. So we already have tiff up here, but we never called its get projection method, but it does exist here and right here, so at line 29 in the header file. So it does have that method. Its projection just contains information about the geographic projection of the geotiff file. So we're going to be using the same projection as the input file, subsetted _final.tiff. So our output geotiff is going to contain the same number of elements, the same dimensions as the input geotiff, but in this case our output geotiff is actually not going to be of integer type. It's actually going to be of a type of byte. Yeah, it's going to be a byte, which is equivalent to car, right? Character. Again, we're just going to have ones and zeros, so I don't see the problem with using that data type. We're going to also get the geotransform, our binary mask, and the number of rows and the number of columns. Lovely. Semicolon. You know, something not right here. I thought this thing was supposed to indent for me. Are you not? All right. I think that's it. Let's just see if this compiles. Okay, so it does appear to compile. I guess what we can do here then is we can try to run this program now. So, right, I just had a sample way to run this program. So what we can say here is the output name of the executable that we gave up here was flood fill, right? So we used the -o flag when we compiled the C++ program, and we called the executable flood fill. So to run the executable, we're going to use /floodfill, and we're going to pass in the name of our input geotiff file that contains the elevations or the heights over the Richat structure. And we're also going to pass in the starting coordinates, x and y. So we'll say 2,000, I think, is a good number when I looked at it, and 1,200. We got to pass in the output directory. We'll just use our current working directory, pwd. And I think that's all we need. So if we can try to run this, if we try to run this and it's successful, it should take some time, and we should see an output file called output_result_Richat_flood_fill.tiff. So let's cross our fingers and try to give this a run. And it's running. Cross our fingers, and once this is done, we're gonna, if we do get the output TIFF file, we're gonna visualize the result to see what it looks like using Python, I guess. We can use the matplotlib plotting routines there to see what our result looks like. Our result, which is a binary mask of ones and zeros. Okay, so it's done, and so we have the file here. It was just created: output underscore result underscore Richat underscore flood underscore filled dot tiff. Okay, it's quite a mouthful. So what we can do here is, and we can see that we have that file. So what we're going to do here is we're going to enter Python, and we're going to import matplotlib. So we can see here from matplotlib.pylab, we can import star. We can turn interactive mode on, so we can actually, pop up a figure on our screen to see what it looks like a pop-up window. We can see the result in a new window, and so that it's not suppressed. So we can call the ion method. We can import numpy as MP. And then we can also import GDAL. So we can see here from OSGeo, import OSR and GDAL. So GDAL, again, that's the Geospatial Data Abstraction Library. So we're going to visualize a result. So we can read it then. We can say here dataset, I don't know, yeah, we'll call it dataset equals gdal.open, and then the name of the file that we have here. So I'll copy that. Okay, so we have a GDAL dataset, and then we want to look at the first band of that. So the array of ones and zeros. We want to see what that looks like. So we can say here data, I don't know, mask, I guess, equals dataset.get raster band 1.read as array. Okay, so we have mask. I don't know, mask.dtype. It's a integer. Actually, it's like a byte. And it has the same input dimensions as our subset underscore final.tiff. Last but not least, let's see what the result looks like. So we can visualize it using mat show. Okay, well there we go. Let's go ahead and add a color bar. Alright, so this is our final result. Let me maximize that. So, yeah, that looks like the Richat structure when we apply the flood fill algorithm to it. So, the areas of ones, that's the yellow that you see here. That's the areas that's been filled in, so to speak. And then, the areas that have not been filled in because the elevation was too high are values of 0. So that's what you see here with the purple. Very interesting result. It looks really neat. You can see here the water is flooding down to the south west, as well as the southeast, actually. And it really is an interesting result. I don't know what it would look like if we were to increase or decrease this elevation threshold, but I suppose if we decrease the threshold, then you might get the entire or more of the image flooded, so to speak, and then if you increase the threshold, less of it would be filled in or flooded, right? But yeah, it's very, very interesting, this result. Let's see that one more time. Okay, so and the color bar, please. Yeah, so maybe in a future video, what I'm going to do is I might try to get digital elevation data, SRTM, Shuttle Radar Topography Mission. I might try to download DEM data over maybe all of sub-Saharan Africa and try to apply a flood fill algorithm on that whole area. It'd be interesting to see. You might be able to see ancient riverbeds or ancient lakes. Maybe not. I don't know. It's probably been filled in with sand by now, probably, but you never know what it may look like. But Maybe we'll do that in a future video, but I think for now we've gone on long enough here, and I think this has been a success. All the code is going to be in the GitLab, or the GitHub, I'm sorry, that's going to be linked below the video, and again, I think we had some fun with using C++ and applying it to ancient history. I had a good time tonight. My name is Jerry. Call me Jerry. And that concludes our second episode of Decoding Ancient History. So, thanks everyone for watching this, and I hope you all are, staying safe out there and trying to be better to your family, taking care of your loved ones. I'm kind of getting off topic here. I'm getting a little sentimental. All right, thanks a lot, guys, and take care. Have a good night. All right, thank you so much. Okay.